Hello everyone, it is our pleasure to present our CVPR paper, DenseCLIP. Language-Guided Dense Prediction with Context-Aware Prompting. The pre-training plus fine-tuning paradigm is recognized as one of the key discoveries that have largely pushed the state-of-the-art for various downstream computer vision tasks. The pre-training step is usually accomplished via supervised classification or self-supervised learning of the backbone model on large-scale datasets like ImageNet. Then, a task-specific module like a detector or a segmentation decoder is added to the backbone, and the whole model is fine-tuned on the target dataset with less training data. Different from conventional supervised and self-supervised pre-training methods only based on images, CLIP is a new framework to learn high-quality visual representation by exploring contrastive learning with large-scale noisy image-text pairs. In this paper, we present a new language-guided dense prediction framework named DenseCLIP. Inspired by the contrastive learning framework in CLIP, we propose to convert the original image-text matching problem in CLIP to a pixel-text matching problem and use the pixel-text score maps to guide the learning of dense prediction models. This is the overall pipeline of our DenseCLIP. DenseCLIP consists of two parts: language-guided dense prediction, which explicitly incorporates pre-trained knowledge from CLIP through the pixel-text score maps, and context-aware prompting, that leverage the visual context to refine the text embeddings and improve the pixel text matching. Before we start introducing the details of our DenseCLIP, let's first briefly review the architecture of the image encoders in CLIP. CLIP has two types of image encoders, VIT and ResNet. The ResNet in CLIP has an extra attention pooling layer that performs multi-head self-attention to both the global feature and the feature maps. In the standard training process of CLIP, the global feature Z bar is used as the output of the image encoder while the other outputs Z are usually neglected. However, we find Z retains sufficient spatial information and aligns well with the text features due to the symmetry of the multi-head self-attention. For architectures like VIT, Z can be obtained similarly by excluding the class token of the outputs. Here we illustrate the main difference between the inference of CLIP and our language-guided dense prediction. While CLIP uses the global feature Z bar to match the text features T, we use the feature maps Z instead. The pixel text score maps have two functions. First, we can concatenate the score maps with the image embeddings to form the input of the task-specific decoder. Second, the score maps can be used to compute pixel text matching loss to facilitate training. Specifically, we view the score maps as a segmentation result from a lower resolution. For segmentation, we build a small segmentation label from the ground truth and compute an auxiliary loss for the score maps. For detection, we construct a pseudo-binary target from the ground truth bounding box and the corresponding class label. We also propose two strategies of context-aware prompting to mitigate the domain gaps by refining the text. The first is pre-model prompting. We pass the features to a transformer decoder with learnable queries to encode visual contexts, and the results are served as the textual contexts. The second choice is to directly use the text features as the queries of the transformer decoder, and the results are used to update the text features via a residual connection. Although the two variants aim at the same goal, we prefer the post-model prompting because it can achieve better performance with fewer flops. We now evaluate our method on ADE20K. A challenging semantic segmentation dataset. We compare the performance of DenseCLIP and existing methods when using the same backbone. The experimental results show that for the same backbone, our DenseCLIP with a simple semantic FPN can outperform the state-of-the-art methods that use more sophisticated decoders by large margins. For object detection, we apply the commonly used RetinaNet and MaskRCNN frameworks. We can observe that DenseCLIP outperforms the ImageNet 1K pre-trained models. Meanwhile, it also improves the vanilla fine-tuning strategy on ResNet backbones. Another interesting usage of our DenseCLIP is that it can be applied to any visual backbone. We can simply replace the image encoder in our pipeline with any other backbone. The results show that DenseCLIP can consistently boost the performance of both ResNet and SWIN transformer, two representative architectures. Finally, we compare the results of different pre-training and fine-tuning strategies on the semantic segmentation task. We show that equipped with DenseCLIP, large-scale vision language pre-training can substantially improve the dense prediction performance over the commonly used ImageNet pre-training. Thanks for watching this video and welcome to scan the QR codes below to follow us.